Hello, and welcome to lecture number 6 in calculus-based physics. Today we are going to switch gears quite a bit. We're going to start looking at the world of physics a bit differently. Up to this point, we've been explaining how things move using the concept of forces. Forces cause things to accelerate, which in turn explains all of kinematics. Now we will switch gears and discuss the world around us using the concept of work and energy. So, what is this quantity that we call work? As we will see, the concept of work bridges the gap between the seemingly very different concepts of forces and energy. First of all, work is not a quantity that something has, like mass or velocity. Rather, it's something that is done to an object. We say that if a force acts on an object while that object undergoes a displacement, that force has done work on that object. Shown in the picture here, these people are doing work to their car as they push it through the snow. Now, suppose we have a box resting on a flat surface as shown here, and that the box is being dragged across the floor by a force that has a constant magnitude and directed at an angle theta with respect to the horizontal. As the box is acted upon by the force, F, it moves through a displacement, S. So just a quick note, unfortunately once again we're going to have to rename displacement. This is an unfortunate notation change that your textbook makes. Now we're going to call displacement S, but it means the same thing as delta X or delta Y. We compute the work done by this force as the magnitude of the force F times the magnitude of the displacement times the cosine of the angle between the force F and the displacement vector. Work has units of Newton meters, which we define as a new unit called a joule. This, as we will see, is the unit of energy. So in this way, we are bridging the gap between forces and energy. You input a force to this equation and you get something out, work, which has units of energy. Work is also a scalar quantity, although it can be positive, negative, or zero. Just to summarize, if you're computing the work done by a constant force, you need the magnitude of the force acting on the object, the magnitude of the displacement, and the angle between the force and the displacement. Now, if you think back to our lecture on vectors, we discussed one way of taking the product of two vectors, the dot product, or scalar product. If you look back in your notes, you'll see that there are two ways of computing the dot product between two vectors. The first involves multiplying the magnitudes of the two vectors along with the cosine of the angle between them. And the other is by multiplying the like components and adding them all together. Now, whenever the force has a component in the same direction as the displacement, it does positive work. This is the case in the figure shown here. In this case, the box is moving under the influence of force F along the x-axis. Force F has a positive x component, which is in the same direction as the displacement, which corresponds to positive work done. Another way of looking at this is the angle between the force and the displacement vector is less than 90 degrees, which will always correspond to the cosine of the angle being positive, and thus a positive amount of work being done. On the other hand, if the force has a component that is in the opposite direction of the displacement vector, that force does negative work. In this figure, the force is opposing the motion of the box, which is moving in the positive x direction. The x component of the force is in the negative x direction, which corresponds to negative work done. Again, another way of looking at this is the angle between the force and the displacement vector is between 90 and 180 degrees. If you compute the cosine of any angle in this range, you will get a negative answer. The only other case is when the force acts perpendicular to the displacement. In this case, the force does no work. This is because the angle between the force and displacement is 90 degrees exactly, and the cosine of 90 is always 0. To summarize, when the force opposes the motion of the object, the work done by that force is always negative. On the other hand, when the force acts in the same direction as the motion, the work done is positive. And finally, when the force acts perpendicular to the work done is then 0. Let's see how this works in practice. Suppose we have a 20 kilogram box that is being pushed along a flat floor through a displacement of 10 meters. If the coefficient of kinetic friction is 0.5, we want to determine the work done by the pushing force, F, the work done by gravity, the work done by the normal force, the work done by friction, and the total work done. First, the work done by our pushing force is computed using the definition of the work done by a constant force. We can simply plug in the magnitude of our force, the magnitude of our displacement, and the angle between the force and the displacement, and we get 1414 joules. Next, for the work done by gravity, we simply do the same thing. First, however, we need to compute the magnitude of the weight, which is simply mg. Then we can plug in the mass, the displacement, and the angle between the weight force and the displacement, and we get 0. Notice that the weight force is always pointing downward, which is perpendicular to the displacement. So we didn't really need to calculate work. We know that any force perpendicular to the displacement always does 0 work. The same goes for the normal force, which is pointed straight up, again perpendicular to the displacement. So the work done by the normal force is 0 as well. Finally, the work done by friction is a bit more tricky. We can start by writing our standard equation for computing work. The force of kinetic friction, which we talked about in the previous lecture, is given by the coefficient of friction times the normal force. So we'll go ahead and put that in. But what is the normal force? In order to figure that out, we need to draw a free body diagram for our box and use Newton's second law in the y direction. I'll leave those steps up to you, but you should find that the normal force is equal to mg, the weight of the box, minus Fn, F sine theta, where theta is 45 and F is the pushing force. As a hint, note that the box is in equilibrium in the y direction. With the magnitude of the normal force in hand, we can simply plug in everything to our equation for work and find that the work done by the frictional force is negative 273 joules, which makes sense because it's negative. In other words, it opposes the motion. Finally, if we want the total work done, we simply add up the work done by all of the individual forces acting on the box. Doing this, we get 1141 joules. Let's do a little thought experiment. Suppose we have a constant force acting on a box through a displacement s. The force is exactly parallel to the displacement, which is directed along the positive x-axis. The work done by this force is just given by our definition of work, Fs cosine theta. However, in this situation, the angle between the force and the displacement is 0, and the cosine of 0 is equal to 1, so we can get rid of that cosine term. Therefore, the work done is just F times S. Now we know that any force can be written in terms of Newton's second law, F equals ma. So let's plug that into our equation for work. Additionally, we can use our fourth kinematic equation to solve for the displacement, S. And we'll plug that into our equation for work as well. Doing this results in a cancellation of the acceleration in our equation. Finally, simplifying gives us our final result. This equation is referred to as the work-energy theorem, and it is extremely useful in dealing with complicated problems. We define the two terms on the right as a new quantity called the kinetic energy. In general, kinetic energy of a mass m is simply calculated using this equation, 1/2 mv squared. And it also has units of joules. This means we can write the work-energy theorem in a slightly different way, mainly that the net work done on an object is equal to the change in the object's kinetic energy. Again, this is called the work-energy theorem. Make sure to burn this into your memories because it is an extremely useful equation. Now, a little more on kinetic energy. As you can tell from the equation for kinetic energy, it is the energy associated with the motion of objects. If an object is moving, it has some kinetic energy. The faster it moves, the more energy it has. Another couple small notes about kinetic energy are that it is a scalar quantity. It has units of joules, just like all types of energy, as we'll see, and it can only be positive. Before we leave the work-energy theorem, I just want to point out that the work-energy theorem is simply a different way of saying the exact same thing as Newton's second law. Newton's second law states that forces cause accelerations. The work-energy theorem says that a force applied over a particular displacement will change an object's kinetic energy, which is the same as saying that it accelerates. We're going to finish up our discussion of work by looking at what happens when a force is not constant. This is going to require us to make use of calculus, but will also allow us to explain things like springs and slinkies. The most obvious case of a variable force is that of the force exerted by a spring. When stretched, springs exert forces that increase the more they are stretched. This behavior cannot be explained with our current method of calculating work. First, let's look a little closer at spring forces. Hooke's law states that springs always want to be in their unstretched or equilibrium length. If springs are stretched, they exert a force that pulls back towards the equilibrium position. And on the other hand, if they are compressed, they apply a force back towards the equilibrium position. Hooke's law gives an equation describing this behavior, mainly that the spring force is equal to kx. Here, k is called the spring constant and is a measure of how stretchy a spring is. High spring constants indicate really stiff springs, like the shocks in your car, and low spring constants indicate very stretchy springs, like slinkies. Finally, x is the stretch distance as measured from the equilibrium length. So the further you stretch a spring, the more it pulls back. Now, how do we compute the work done by such a variable force? Let's look at a simple example before graduating to springs. Suppose we have a constant force acting on some object. A constant force doesn't change as a function of position. Therefore, the graph of this force as a function of position is a flat line as shown here. If we compute the area under this line, we simply have a rectangle, so it's base times height. The height of the rectangle is the magnitude of the constant force, and the base is the displacement of the object, s. This is exactly our definition of work, a force through a distance. Therefore, the area under the curve of a force versus position graph is work. This means that we can write the work done by any force as an integral of force over position, as shown here. This equation works for both constant and variable forces. However, it's a complicated and unnecessary way of dealing with constant forces, so we'll only use it for variable forces. Now suppose we have a spring of spring constant K that is initially unstretched in its equilibrium position. Then we apply a force and stretch the spring. Plotting this force as we stretch the spring more and more gives us a plot that looks like a line. This can be explained because for a spring, F equals Kx, which is the same form as the equation of a line, y equals mx plus b, but with the y-intercept simply equal to 0. Now the area under this graph is equal to the work done in stretching the spring through the displacement x. Since we have a triangular area, you could figure out the work done without using calculus, since the area of a triangle is just 1/2 base times height. But let's do the calculus as an exercise. We first write the definition of work done by a variable force, mainly that work is the integral of force over distance. Then we can plug in Hooke's law for our force, Kx, and set limits of integration. Our lower limit is going to be when the stretch distance equals 0, and the upper limit is going to be when the stretch distance is some arbitrary x value. I'll let you work out the steps of this integral, but using the power rule you should just get 1/2 kx squared, exactly what you'd expect by computing the area of a triangle. Now we didn't make any crazy assumptions about this spring, so we don't have to compute an integral every time a spring pops up in a problem. We just know that the work done in stretching a spring is 1/2 kx squared. Let's see how this works in practice. A block of mass 0.5 kilograms is attached to the end of a spring of spring constant 200 newtons per meter, which is compressed by 0.25 meters from its equilibrium length. The block is initially at rest against the spring. The spring is then released and the block is shot away from the spring. Determine the velocity of the block after the spring is released. Here we have a variable force from the spring being applied to a block which is then accelerated. The easiest way of determining the final velocity is by using the work-energy theorem. Note that we can't use Newton's second law because that only works for constant forces. Writing out the delta here for kinetic energy, we have the net work is equal to K final minus K initial. But we know that the initial kinetic energy has to be 0 because the initial velocity is 0. So we have the net work is equal to just K final. Now the work done on the box is just the work done by the spring, 1/2 kx squared. And that should be equal to the final kinetic energy of the box, 1/2 mv squared. Then we can rearrange to solve for the final velocity, which I find to be 5 meters per second. I want to finish the lecture with a quick note about a quantity called power. We've seen how to compute work, but what if work is actually changing over time? The rate at which work is done on an object is what we define as power. The average power during a particular time interval, delta t, is simply the change in work over the change in time. Power is measured in units of joules per second, which we define as a new unit, watts. For comparison, 1 horsepower is equal to 746 watts. Analogous to kinematics, the instantaneous power delivered is just the derivative of work with respect to time.